the last thing I'd like to do, now that we've talked about how the async task framework implements the half-sync, half-async pattern, now that we've shown the implementation of async task, now that we've taken a look at some of the implementation elements of the Hammer framework, I'd like to sort of evaluate all the different frameworks and compare and contrast them. And this will really sort of be the last bit of coverage we do for Java and Android concurrency. The other stuff that we'll do, we'll talk about other things. You know, we may talk more about patterns. We may talk about other things in Android. But this will give you a good feeling for how to wrap it all up. So what we're going to do is evaluate these frameworks, but we're going to do it in the context of the threaded downloads application, just to give it something concrete to talk about. So let's first talk about the different frameworks. And we're going to compare and contrast them along a number of different criteria. So we're going to have usability from the point of view of how easy is it to use them. That's one usability dimension. And then we're also going to have usability in terms of complexity, which means can they do complicated things, right? There's different forms of usability. Sometimes usability says, let's make easy things easy. But sometimes when you optimize for making easy things easy, you make hard things really hard. So a good example is Java's synchronized methods. So Java's synchronized methods and monitor objects that are built into the language makes simple forms of concurrency really simple. But more complicated forms are hard, as you guys discovered when we did the specific notification pattern, where you had to do a lot of complicated programming to make that work right. Sometimes, conversely, there'll be abstractions that are harder to learn, but once you know them, it's a lot easier to do complicated things. I remember one time I was at I was talking to some very famous people. Well, one of them's dead, so I can give his name. Dennis Ritchie. I was talking to Dennis Ritchie, and he was beating up on the middleware I was working on at the day, which was Corba. And he was like, you know, look at the manual for Corba, right? It's so big. And he's like, and look at the manual for Plan 9, which was his operating system at the time at Bell Labs. It's so small, you know. And what I wanted to say, but I never said, but I should have said, look at the manual for building and flying a paper airplane. Look at the manual for building and flying a 747. Why do you think one of them is bigger? Right? Because it does a heck of a lot more stuff, you know? So it's not always the case that simplicity is good, but you have to take it relative to what your goals are. And if you're trying to do more complex things, giving somebody something really simple actually makes their life more complicated, because either they can't do it or they have to write so much more code that it becomes even more complicated. I'm having a debate with some other folks, more contemporary folks, who believe in that their argument is open systems are bad if you're trying to build software that is hard to tamper with. So there's a whole philosophy called anti-tamper, right? Most of the stuff we do day in, day out, people tamper with it all the time. Right? There are hackers on your system, and you just sort of shrug your shoulders and you say, oh well, you know, I don't have that much important stuff, so I don't care. There are some places where people care a lot, right? National defense, banking, right? People care a lot. So there's an attempt at trying to make things in an anti-tamper-like way, which makes some sense. But if you're not careful, you can get confused, right? So one thing says, if you build your system out of reusable parts that are modular, with well-defined interfaces and using standard protocols and so on, that might be good from one perspective, but it makes it much easier for people to tamper with, because all they have to do is know the magic pieces, and they can break in, right? If they can take one part and test it in isolation, they could find a way to exploit it. And then once they've got that, they've got the whole thing, because you built it out of reusable parts. The problem is that the alternative to this, which is, you know, well, what is the alternative to this? Well, if you don't want to use modularity, you don't want to use reusability, you don't want to use flexibility, you don't want to use interoperability, what are you going to do? Well, what you're going to do is you're going to build everything in a random, ad hoc, ball of spaghetti way, on the offhand chance that the bad guys will get burdened down with this unbelievably convoluted mess you've created and will give up and won't try to break into your system. Well, I've got news for you, right? They're very patient, number one, and they'll probably figure it out. But the real problem with doing that is, who will actually pay the price of the unbelievably convoluted, spaghetti-laden software? it might slow the bad guys down by a week or two. But who will pay the price over time? The users who can't figure out what the hell the system does, right? So operators won't understand it. The developers won't understand it. They'll have to reinvent everything that we've come to know and love off the shelf again, probably poorly because they don't really know what they're doing, and so it becomes this interesting, philosophy discussion. So the right approach is probably to use the open stuff as much as possible and then figure out where your vulnerability points are, and then go in with careful, targeted investment and build, high fidelity hardware-based encryption or some other security mechanism for the parts that really matter, the critical technology part, and make those things be the stuff that you really protect. Anyway, the whole point of that was that there's differences between simplicity and complexity, and sometimes one size doesn't fit all. And so something that's more complicated at first glance may actually be simpler when you try to use it in a larger scale. Okay, so those are usability, scalability, hopefully that's really clear, flexibility and efficiency. So we'll talk through these things. So the async task stuff is very good because it scales up pretty well, and it's relatively easy to use once you understand it, right? Once you understand how to subclass and override a few methods, which is just the template method pattern, so that's easy. It works pretty well, and it is going to simplify development of a variety of use cases. By being able to plug in your thread pools, you can let it scale to a larger number of cores, which is good. Unfortunately, it's not ultimately flexible, right? These are the design trade-offs we always have to confront. So it's really only intended for interactions between the user interface thread and background threads. It's not intended for interactions between arbitrary threads, so it's not all that flexible. And it's maybe not the most efficient thing because, as we talked about, there are these context switching overheads and data copying and data movement and synchronization and so on. So there's extra levels of indirection, and there's costs for moving stuff around. So that's kind of async task against those criteria. Let's take a look at the other approaches, which are both in the Hammer framework, posting runnables and sending messages. So posting runnables is really simple, right? You just say, make me a runnable and post it. What could be easier than that, right? So that gets 3 stars for usability for simple use cases. When you start trying to use it for complicated use cases, though, it doesn't really work very well because you localize all the decision making at the point when you invoke the call. So there is not an easy way to be able to have the receiver do anything sensible to modify what it got. It just blindly runs it. And so it's also not very flexible. It doesn't really scale up very well. If you want to make multiple threads, you have to spawn the threads and manage them and so on. It doesn't do it for you. And let's see. But it is very efficient because it doesn't have much overhead. Message passing, in contrast, is very flexible and efficient. Again, for the same reasons, you can rearrange things and wire them up in all kinds of crazy ways. You can pass arbitrary data. You can have peer-to-peer conversations where you're sending messages back and forth between different threads, and there could be many of them. But you have a lot of programming to do. So you have to worry about writing the handle message hook method. You have to coordinate anything having to do with thread pools, and so on and so forth. So as you can see, this is just the classic Consumer Reports kind of a diagram. There's nothing here that gets, 3 stars, which is the max in this case, across the board. And so depending on what it is you're trying to do, you might gravitate to one model or another. Again, for my money, most of the time, async task is fine. So it kind of depends on what your requirements are, depends what your expertise is, it depends on what your expertise of your developers are. One of the things you'll discover, many of you already have probably discovered this if you do consulting work, but you'll find that not everybody in the world had the benefit of a Vanderbilt education with courses on patterns and frameworks and concurrency and stuff. And so things that you might take as being second nature and intuitive, you'll have to spend a lot of time explaining to people to help them understand what it is that they need to do. And of course, it's nice nowadays because you can point them to literature on patterns and places to learn this stuff. But a good rule of thumb is it's the job of the smarter person to make things easier for the people who haven't reached that level of accomplishment yet. And so a classic thing to do is build layers of abstraction that shield most people from the details that someone who's more accomplished might revel in and enjoy. I worked on a project many, many years ago, 20 years ago, with a company called Siemens. in Germany, and we were building stuff for them, and they were having a real hard time understanding concurrency. And so they would come and ask us, how should we do concurrency? And we'd say, oh, well, there's the active object pattern and the command processor pattern and this pattern and that pattern and thread-specific storage, and their eyes would glaze over and they'd go away for a while, and then a week later they'd come back and say, how do you do concurrency? Right? And it was clear we were not getting anywhere trying to teach them patterns. So what we did is we built a processing engine, which was called the worker pool model, which is basically the command processor pattern. And we said to them, if you want to run something concurrently, package it up in a message or an object and send it to this engine, and it will queue things up and run them for you. And they were happy with that, right? It wasn't the world's most scalable and efficient thing. It was actually almost exactly like the Java executor framework. It was just done in C++ in those days, but it's the same idea. And that made them happy, right? Because they didn't have to think too hard. They just said, here's a message, or here's a runnable, whatever, send it to this guy, work gets done, I get a result back at some point. And the solution there was not to try to teach them about complicated concurrency patterns. It was to use our knowledge of complicated concurrency patterns to put together a framework that was really simple to use. And that got them where they needed to be. And you'll often find that in practice. Okay, so to summarize this, the threaded downloads app implements these different concurrency models using the different frameworks that Android provides you. And they share some things in common. All three models run long duration operations in the background. Short duration stuff runs in the UI thread. That's just an Androidism. We can't do much about that. There are also some differences. Background threads and UI threads communicate in different ways. Runnables, messages, method calls, right? All that stuff is done in different ways with different trade-offs. In the Hammer framework, the background threads explicitly communicate to the UI thread. So background thread will go ahead and send runnables and messages through handlers to the main thread, which then dispatches those things. Not quite sure what that means. That's weird. The async task solution has background threads explicitly communicate to the user interface thread. You don't have to do it directly, and that's because it's done for you by the magic of the framework implementation, which does it through all these different hook methods that get called back with future tasks and worker runnables and that kind of stuff. And as we saw, each solution has pros and cons. Probably the most useful thing you can take away from the whole class, if you don't remember anything else, is that good design is about trade-offs. And you very rarely can maximize everything at the same time. Oprah once said, you can have it all, you just can't have it all at once. And that's probably true here. So the knowledge of patterns, great software architect, Oprah Winfrey, she's little known, that's where she really made her money. And understanding requirements is crucial, and of course knowing patterns is important, and knowing how to map those patterns to frameworks is important. Now, in this class, you've got a little bit of experience building some frameworks. You've got a lot of experience. You're learning to use the frameworks and understanding why they're useful. So that's probably where most things are today. The more you work on technology infrastructure projects, the more you need to understand how to build the frameworks. The more you're building applications, the more you're using the frameworks. But as we saw with stuff like the task gang stuff I showed you, once you understand frameworks, you can use lower level frameworks like the Java executor framework in order to build meso level frameworks like the task gang framework, which you can then use to assemble higher level applications much more rapidly. And I'm having fun with Nolan, as you know, one of the TAs. He and I are building this cool framework for doing the image downloading stuff we've been looking at using the task gang framework. And of course, it's just so cool because everything just falls into place. And we've got a little demo which we might show you later that now can either run as just a standalone Java application or be hosted inside of an Android application for being able to take a big chunk of URLs and then download them all concurrently and then display them in a list view. So it's cool because it's the same piece of code running in both places. It's using the frameworks. It's using the task gang framework. It's using the Android frameworks, the Java frameworks, all these frameworks working together. And the actual amount of code we have to write is very, very small. It's all localized to the application logic, not to the infrastructure processing.